One of the ways to obtain accurate results from SolidWorks simulation is to accurately depict what the material property of the model is in real life. Often enough, the library is a generic material brought in from the machinery's handbook, and this may or may not represent the true material being used in production. This video will serve as a quick guide on how to translate material properties specifically into SolidWorks simulation and what they all mean. The values to define the material listed on the manufacturer's website are often listed in a different format than inside of SolidWorks simulation, and this can lead to some confusion for some designers who have limited knowledge of material properties. For basic static FEA simulation, you need density, elastic modulus, Poisson's ratio, and yield strength to perform a simulation. So what are all of these numbers and where do I get them from? The first one is density, and density is simply a degree of compactness, and most people know what this property is already. Poisson's ratio is simply a measure of the Poisson effect, or the phenomenon in which a material tends to expand in directions perpendicular to the direction of compression. The opposite is also true, like when you stretch a rubber band and the band becomes thinner. Most materials have a Poisson's ratio between 0 and 0.5, steel being 0.3. This is almost always listed by the manufacturer or it can be found from similar materials. Elastic modulus goes by several names and has several forms that we can graph and visually learn about. It may interchangeably be called the modulus of elasticity or Young's modulus. Simplified, the elastic modulus has three forms that you will see listed on a material that simply defines the material's ability to resist permanent deformation or damage when acted upon by a load. These three are Young's modulus, shear modulus, and bulk modulus. Sometimes people refer to the modulus of elasticity as simply Young's modulus since it is the most common way to measure elasticity. Young's modulus is what will most commonly be listed because it defines how a material stretches in one direction when pulled apart in tensile loading or pushed together for compressive loading. And as engineers, we typically care about this because of how we want to load parts. The bulk modulus is simply Young's modulus in all directions, and this is harder to measure. Shear modulus is also called the modulus of rigidity and describes a material's tendency to shear or fracture with opposing forces offset very close to each other like scissors tearing through paper. All of these moduli are a ratio of two specific values, stress over strain in some direction. Stress is the measure of built-up internal forces or force over area in a material's molecules pressing against each other, and strain is a measure of how far an object deforms from one place to another. We can measure strain with sensors for verification in manufacturing by pasting them onto a part and applying a load to detect how far the part moves under load. These two values are what we are typically trying to find in SolidWorks simulation. The last value you're going to need is the yield strength, which is a stress value. It's also called the proportional limit, the yield point, and yield stress interchangeably, and refers to the value of stress in which a material will no longer deform elastically and permanent damage occurs. Brittle materials do not have a true yield strength and will just fracture, which we will talk about in a moment. As engineers, we typically design parts to avoid this stress level by a margin of error called the factor of safety. With these four numbers, we can run a study and perform an analysis to find stress and strain and create safe parts. Some additional numbers that might be listed are the tensile strength and compressive strength, which dictate what stress level a material will max out at, whether permanent damage has occurred or not. This is also called the ultimate strength. This is a number which is useful to have when defining when a part has fractured in loading, as some parts are designed to fail to protect other parts. The ultimate strength and yield strength are typically different on ductile materials, but brittle materials usually do not yield noticeably and fail at their ultimate strength. Many manufacturers list the material tensile strength and compressive strength as their material's ultimate strength in specific types of loading because that is how the samples were tested in a laboratory. These numbers are not required, but it is recommended to obtain them. If you're doing a static stress analysis with some thermal loading, you need the thermal expansion coefficient, or the rate at which a material grows per unit length at certain temperatures, to complete this type of analysis. All of these values can be found or interpolated through lab data, which can be found in a couple of places. If the manufacturer or distributor of the material does not have data, you could check the Materiality web portal available through SolidWorks simulation packages, or through a reliable source like matweb.com. I hope this information helps newer designers to digest what these numbers mean and how to put the strength of your material into SolidWorks simulation. For material models outside of linear models, We discuss this in another video on the TPM Solutions YouTube channel called Can SolidWorks Handle My Material? Thank you for watching TPM's 3 Minute Thursdays, and we'll see you next time.